Hello class, and welcome to the third module of the course where we transition from thinking about environmental economics to thinking about resource economics. In the weeks to come, we're going to have some video lectures on both renewable resource economics and non-renewable resource economics. But the purpose of today's video is largely to distinguish what makes resource economics different from environmental economics. And a lot of that depends on whether or not the problem is dynamic. And once we clarify what that means, we're going to move on to discussing the concept of dynamic efficiency, which is going to be so important for our understanding of resource economics in general. And is also going to tie into our other ideas of efficiency that we've had throughout the rest of this semester. So the overview of this class is going to address four primary topics, the first of which is the concept of dynamic efficiency. So we've already thought of what efficiency means in a static setting where we want to set the marginal benefit equal to the marginal cost. The question is now, first of all, what does dynamic even mean? Second of all, when we have multiple time periods, how do we think of efficiency in that setting? Secondly, we've already addressed in this class how scarcity creates value and scarcity then creates prices, but how can we put a price on scarcity itself? And that's going to be an important component when we think about non-renewable resources, which are by definition becoming more scarce the more we extract. We're then going to discuss an overall system for classifying resource scarcity, and then move on to concluding the lecture by considering how we most efficiently use and manage our non-renewable natural resources. We're going to think of some different rules that we can apply to the management of non-renewable resources, both from we'll call it just naive perspective, where we don't really consider the economics of scarcity, and then how that rule changes when we really think as economists. So hopefully this will all tie together well, and we'll be able to connect our concept of dynamic efficiency and the price of scarcity to our management of non-renewable resources. So to come back to that key term from the previous slide of dynamic, we're going to think of problems as being dynamic, not when they have payments or outcomes that occur over time, but when they require or involve decisions that need to be made over time. And so this will be made more clear in the coming slides. We'll come up with some different examples and ways that we could classify some problems as dynamic and some as not dynamic. But in general, we want to think about the role of time as both pertaining to the state of the world, the consequences, as well as our decisions and our actions. And a problem is going to be dynamic, not when there are changes to the state of the world over time. We've already thought about that in this class when it comes to discounting the future and whether we use a finite time horizon, an infinite time horizon, or a lump sum payout. But a problem is going to be dynamic when those actions, when those decisions need to be made over time. And so once again, we have finite time horizons. We know how many periods into the future the problem exists. We have infinite time horizons. I mean, that's going to exist in perpetuity. And a fundamental component here of scarcity and dynamic decisions is that if we're using up resources, now there are fewer resources available in the next period. So there's a connection between the state of the world in one period and the state of the world in another period. So that connection between the state of the world in one period and the state of the world in another period can be thought of as a systematic link. And when we want to assess whether a systematic link is present, we want to ask ourselves, does what I do today affect what I can do in the future? Not just what the world is going to be in the future. Remember, that's not going to be dynamic. That's just involving the state of the world over time. We want to think about decisions that we make across time. And we want to think about a problem as being forward-looking and not backward-looking when it's dynamic. So are you picking the optimal stream of actions for your entire lifetime, or are you just making a decision based on the state of the world today, which is a product of decisions which you've made in the past? And so we really here want to focus on that link between decisions across time and not just decisions based on the state of the world, which is based on decisions which you made in the past. And so we'll come back to this example with a slightly different context later on in the lecture, but if we think about being Tom Hanks in this really outdated example, but you're cast away, you're trapped on that desert island with your good buddy Wilson, and you want to think about how you can manage the limited firewood on the island. That's clearly not infinite, it's clearly not unlimited. There's a definite spatial scale to this problem here. And you know that some of the wood is going to regrow over time, but it's going to take time for it to regrow. And you get utility or happiness from either burning the wood for heat or using it to make a boat. You need to base your decision of how much to harvest at any given point in time based on what you expect your needs to be in the future. So how much wood am I going to need to stay warm in the future? What kind of boats am I going to need in the future? As well as considering that systematic link between the regenerative capacity of the wood over time. So there's, once again, here different components of being forward-looking and a systematic link between decisions which you do today and what you can do in the future. Now, a key component to that problem, and in part what makes it dynamic, is that scarcity exists and that it clearly matters for determining whether a problem is dynamic. And so if the resources are not scarce, then you just make a series of static decisions and you don't care about the future. What you do on day one doesn't impact your choices on day two, and you just maximize your net benefits at every given time period. And if you could think about here, if you're the last or one of the only humans left on Earth, and you're not just one human trapped on a small island, you're not going to care about how quickly you cut down trees because you're never going to exhaust the total number of trees on Earth between you and only a handful of other people, because the time that it would take for you to cut down all the trees, some of the trees would have grown back. And so there is no systematic link between what you do today and what your actions may be in the future. And so it's not a dynamic problem anymore. So to consider an example here that may help us clarify what types of problems are dynamic and what types aren't, let's think about a middle schooler, elementary school kid traveling to school. So they're going to school, they don't like taking the same route to school on 2 days in a row. And the question is then, is this a dynamic problem? So you certainly have to choose which route you're going to take on each day, in that if you take route B on Monday, then you would need to take route A on Tuesday and route B on Wednesday. And so there is decisions being made over time here. But we could also choose the other pattern of choosing route A on Monday, route B on Tuesday, route A on Wednesday. So the question is there a systematic link then between those decisions? And if there is a systematic link, is the problem dynamic? And so this problem is not dynamic, even though there seems to be a connection between the decisions which we make at any given point in time. However, while there is a link between the actions chosen yesterday and today, since you are equally happy with strategy 1 and 2, you can randomly choose what to do on Monday, and then Tuesday and the rest of the week is just going to be backward looking and not forward looking. And so we need both of those components for it to be dynamic. There needs to be a systematic link between decisions which are made across time, as well as forward looking decisions being made by the economic agent. And that forward looking is a way of kind of enforcing the standard that the link between decisions is between the decisions themselves and not between the state of the world. And so in this case, because what you choose on Monday creates a state of the world which is different on Tuesday, then the decision that you're making on Tuesday has nothing to do with what you're going to do in the future. It's strictly based on, if I choose to take the same route that I took the day before, I'm worse off. And if I choose to take a different route, then I'm going to be better off. And so the decision that you're making isn't forward looking, it's strictly made in response to the state of the world from the decision that you made on Monday. Now, if we add one extra wrinkle to this example, we can see how it could become a dynamic problem. And for that just additional complexity, let's assume that you don't like taking the same route to school on 2 days in a row, and you know that the road is closed on Friday for route B. So what do you do? Because route B is closed on Friday, you have to take route A on Friday, which means that you have to choose wisely on Monday, and that you are making a forward-looking decision where the decisions which you make in the future are going to be based on taking that one specific route on Friday, and that linkage between the decisions of taking alternating routes before that point in time. So now that we know what dynamic means, what does dynamic efficiency mean? Well, efficiency in a static world is just marked in economics terms where the marginal benefit of a decision equals the marginal cost. And so when we have supply and demand, where demand equals the marginal benefit, supply equals the marginal cost, then our efficient point is going to be at the intersection of those two curves, which sets marginal benefit equal to marginal cost and maximizes our total economic surplus. So how do we achieve dynamic efficiency? How do we set our marginal benefit equal to our marginal cost in a context where the decisions in one time period are going to be linked with the decisions in another time period, and ideally in a forward-looking framework? We're going to have a dynamic efficient allocation, which will then maximize the net present value of net benefits over time. So we're getting at this same connection between efficiency and maximizing net benefits, but now there's just a temporal component to it, which is going to require discounting the total future stream of net benefits, not just the net benefits in one time period. So let's consider the efficiency of the extraction of a natural resource. So in a single period, efficiency, as we know, is just going to be defined by the point at which the marginal benefit equals the marginal cost. So let's assume that we have a constant marginal cost here at $2. So whether we extract 1 ton of the resource, 2 tons of the resource, 4 tons of the resource, we're going to have that constant marginal cost of $2. And we're going to have a declining marginal benefit, which is consistent with both satiation, that we have enough of it at some point in time, that there's the law of diminishing marginal utility. Each additional unit's bringing us less happiness, less utility. So we have our decreasing demand, marginal benefit, willingness to pay curve, they're going to cross at some point. In this case, when the price is equal to that constant extraction cost of $2, which would be at a quantity of 15. So the total benefits there would be the area underneath the demand curve. So this should look a little bit like exam number 2, one of the questions. And that's not just the net benefits, that's going to be the total benefits, the whole area underneath the demand curve up until the quantity which we've decided to extract. And the net benefits are going to be the area underneath the demand curve up until that quantity, but above the total cost. And so if it costs $2 per unit to extract and we extract 15 units, then we're going to subtract $30 from that total benefits to give us the net benefits. So if we move to 2 periods, then ideally we would consume the quantity which would maximize our net benefits in each period. And so in period 1, that would be 15 units. In period 2, that would be 15 units, since we know that's going to be the efficient allocation, which is going to maximize our net benefits. However, if the stock of the natural resource is greater than 30 and there are only 2 periods, this is no problem. We would consume 15 units in each period. But if the stock is less than 30, then we can no longer consume 15 units in each period, and we have to come up with a rule or a method of allocating that stock across the different time periods, which is going to take into account our time preference as well as the scarcity of that resource. So let's just stick with this example and assume that there are only 20 units of the resource that are available. So if the discount rate is 10%, how do we allocate the scarce resource between the 2 periods? So hopefully it's clear now that if optimally in a world without scarcity, we would desire 15 units in each time period, and there's only 20 units total, we're going to have to make some trade-offs here about how much we can consume in time period 1 versus time period 2. Are we going to equally separate out those 20 units between time period 1 and time period 2 and consume 10 units in period 1 and 10 units in period 2? Are we going to consume our optimal amount in period 1, 15, and just allow those 5 extra units to be consumed in period 2? Or are we going to meet somewhere in the middle and use the discount rate to maximize our net present value? And hopefully by now the intuition is kicking in that we're going to follow that third, more nuanced approach of creating a dynamically efficient allocation. So before calculating any sorts of answers to this problem, let's think about the intuition behind the role of the discount rate. So at this point in time, it's been a couple weeks since we've discussed discounting in economics, but hopefully the intuition is still relatively fresh in your mind that a positive discount rate means that we're going to place more value on costs and benefits incurred in the more immediate future. And so if we think about crab fishers in Alaska, if their discount rate is high, does that mean that they are more likely to harvest more crabs in the first period, harvest less crabs in the first period, or harvest the same amount of crabs in the first and second period? So hopefully it's intuitive to you that since we place more value on costs and benefits incurred in the more immediate future, a high discount rate is going to imply that we're going to harvest more crabs in that first time period. So if we have a discount rate of 10%, it means we're ideally going to consume more of the resource in the first period than in the second period. So we're not going to equally split our consumption of those 20 units or extraction of those 20 units across those 2 time periods. But to know how we're going to share that extraction across those 2 time periods, we need to know a little bit more about the marginal benefit curve and the marginal cost curve. So because the marginal cost curve is constant at 2, we're just going to have MC equals 2. And because the marginal benefit curve is downward sloping with a positive intercept of 8, we're just going to think of our traditional algebraic formulation of a line where y equals mx plus b, and our dependent variable here, marginal benefit, is going to equal that positive intercept of 8 minus the slope, how quantity changes as price changes, multiplied by our independent variable of quantity. So having calculated the marginal benefit and the marginal cost, we can calculate the marginal net benefit. So this should seem similar to our Cosian bargaining framework, where we had columns in those tables not only for the marginal benefit to the firm, but the marginal net benefit to the firm, subtracting the marginal cost from the marginal benefit. And because the marginal cost is constant at 2, and because the y-intercept is 8, our y-intercept of our marginal net benefit curve is going to be 8 minus 2, which is 6. And it's going to have the same slope, that same 0.4 slope. So if we multiply the x-intercept here of 15 by 0.4, we get the y-intercept of 6. And we can see that we also have the quantity going in both directions on the horizontal axis here. So in black, we have the marginal net benefit in period 1, the quantity extracted in period 1, and then in red, we have the marginal net benefit in period 2 and the quantity in period 2. And so graphing that marginal net benefit in period 1 is pretty straightforward. And you can probably take a guess about how we're going to start graphing the marginal net benefit in period 2. So in period 2, we're just going to take that same marginal net benefit equation from period 1, and we're going to discount it. We're going to discount it by the number of years into the future that it is. And so in this case, we are going to find our y-intercept of, once again, 6, and we're going to discount that in the future. So set it over 1 plus the discount rate raised to the number of years. In this case, it's just 1 year in the future. And that's going to give us a new y-intercept for our period 2 marginal net benefit curve of 5.45. And we would apply the same sort of transformation to the rest of the marginal benefit, the net marginal benefit curve equation, as we'll see in a slide or two from now. But once we plot that out on this graph, we can see where these two curves would cross, where the present value of the marginal net benefit in period 1 would equal the present value of the marginal net benefit in period 2, and what quantity we would extract in both time periods. As you can see here, it's pretty close to being equally split between period 1 and period 2, but we're extracting slightly more than 10 in period 1 because of that time preference, because we're discounting the future by 10%. So if we were to look at this in equation form, once again, it's pretty straightforward. We have our marginal net benefit. Our price is equal to negative 0.4Q plus 6. And since we're not discounting that, that is the present value of our marginal net benefit curve as well. In period 2, we have our marginal net benefit curve, which is the same as in period 1, but we need to discount it. And so we divide all of that by 1.1, which is really just 1 plus 0.1 raised to the 1, like we're making that present value, future value conversion that we did back in week 2. And once we do that, we find that the slope is now negative 0.36 and the y-intercept is 5.45. So there's a couple conversions that we need to make. We need to transform our marginal benefit curve into a marginal net benefit curve. We need to transform our marginal net benefit curve into our present value marginal net benefit curve, and our marginal benefit curve, our marginal net benefit curve in period 1 is going to equal our marginal net benefit curve, the present value in period 1, but in period 2 we just need to discount the marginal net benefit curve to get the present value of the marginal net benefit curve. And so once again, we can see that graphically this would imply that we're extracting more than 10 units in period 1 and less than 10 units in period 2. So how would we solve this numerically to find that exact answer? Well, it's just going to be algebra and systems of equations. So we basically have 3 equations and 3 unknowns. We don't know the quantity we extract in period 1. We don't know the quantity we extract in period 2. And we don't know the present value of the marginal net benefit, which is going to set those two equal. And so the first key to solving this problem is to recognize that the quantity we extract in period 1 plus the quantity we extract in period 2 is going to equal the total amount of that quantity if there are only 2 time periods to extract that total quantity. And so we can then substitute that to solve for either Q1 or Q2 and set Q2 equal to 20 minus Q1 in this example. So we then have our present value of the marginal net benefit curve in period 1. We've got the same curve in period 2, but it's discounted. And we're going to know that we're going to maximize our net benefits, the present value of our marginal net benefits, when these two curves are going to be, when these two values are going to be equal. And so we can set these two equations equal to each other and then plug in our resource constraint, in this case for Q2, and we have negative 0.4 Q1 plus 6 equals negative 0.36 times 20 minus Q1 plus 5.45. And we can simplify that and solve for Q1, and we get Q1 is equal to 10.2 and Q2 is equal to 9.8. We add those two together and we have 20. So once again, just relatively simple algebra. I don't need to overthink this part of it. So why do we solve it by setting the present value of the marginal net benefit curves equal to each other? Well, our end goal is to maximize the present value of the net benefits, being maximizing the size of 2 triangles, right? So both of the triangles in the static framework. And if there's no scarcity, it's just a series of static problems, consume 15 periods, 15 in each time period. But if there is scarcity, we just know that the nature of this problem is going to result in depleting the entire resource at the end of all time periods and consuming more in the present time period than in the future due to positive discounting. So we set these two curves equal to each other as a way of maximizing our total net benefits. And we'll give some graphical demonstrations here in a second to show why this is the case. But this is just basically another equimarginal principle. We had our first equimarginal principle that our marginal net benefits, our net benefits are going to be maximized when we set marginal benefit equal to marginal cost. We had our second equimarginal principle that we're going to minimize the total cost of pollution abatement when we set the marginal costs equal across firms. And now we have our dynamic equimarginal principle, which is going to state that our present value of our marginal net benefits across all time periods is going to be maximized when our present value of the marginal net benefits in each time period is equal. So we know that we're going to extract more in period 1 than in period 2 due to positive time discounting in our time preference. And yeah, really this hopefully should be review for you at this point. So I won't spend too much time going over this. All right, so graphically, let's demonstrate why this dynamic equimarginal principle would maximize the present value of the net benefits. So we can see in this framework, in this graph, which is going to display the answer which we calculated, that we are fully maximizing all opportunities from trade with ourselves across multiple time periods. That there's no area in which the marginal cost is greater than the marginal benefit, and there's no opportunities for trade which we haven't exploited. So what if we choose another allocation? So for example, if we consume 12 in period 1 and only 8 in period 2. Well, looking at the present value of the marginal net benefit curves, we can see that we have greater area under the present value of the marginal net benefit for period 1, but we have less of an area under the present value of the marginal net benefit in period 2. And in fact, we have sufficiently less area, so pretty much everything from 10 over to 12, that loss in period 2 is greater than the gain in period 1 by the area of this deadweight loss unexploited gains from trade triangle. And so we have deadweight loss from overconsuming in period 1. Similarly, if we underconsume in period 1, then we're going to have the same problem. We're going to have deadweight loss from underconsumption in period 1, overconsumption in period 2. We would be made better off by trading some of that consumption from period 2 to period 1. And so when we set those curves equal to each other and extract according to when the present value of the marginal net benefit curves are going to be equal to each other, that's when it's just the dynamic analog to setting the marginal benefit curve equal to the marginal cost curve and realizing that the sum of consumer surplus and producer surplus is going to be maximized at that point. So thinking back to Econ 101 in our definition of opportunity cost, what we give up to get more of something else, we can think of the present value of the marginal net benefit of the other period as the opportunity cost of extracting in the present period. So to get more extraction in a given time period, what we're giving up is extraction in the future. And so since in this particular example, there's no benefit to period extraction or consumption in period 3, we're going to fully deplete the resource by the end of period 2. And anytime we would extract the resource such that the present value of the marginal net benefit in period 1 does not equal that in period 2, that's basically going to be the same thing as extracting where the marginal benefit is less than the marginal cost. Because the present value of the marginal net benefit in the other time period is essentially the opportunity cost of extracting in the present time period. So hopefully you've got an idea about intuitively what would happen to that optimal allocation of resource extraction across the two time periods if the discount rate were to change, either to increase or to decrease. And so let's say that we increase the discount rate dramatically from 10% to 50%. Well, now we are dividing our present value marginal net benefit curve in period 1, not by 1.1, but by 1.5 in the second time period. And so our y-intercept shifts from 6 in period 1 down to 4 in period 2. And because the slope of that curve is also getting flatter and the y-intercept is shifted down, the intersection of these two curves is going to shift even further to the right. And so now we're consuming even more in period 1 and even less in period 2. On the other hand, if we decrease the discount rate from 50% or 10% down to 0, then we are just dividing our present value of our marginal net benefit curve in period 1 by 1 plus 0 raised to the 1 in period 2. So if we're dividing that curve by 1, it's just going to be the same curve in period 1, and they're going to intersect at a completely equal allocation between the two time periods. And so in this case, there'd be an equal amount of extraction in each time period, implying that there's no time preference. And we can just treat this as a series of static problems. All right, so hopefully that clarifies the first bullet point from the overview for today's class on what classifies a problem as being dynamic and what dynamic efficiency really means, and how we can use that dynamic equimarginal principle to calculate the most efficient extraction solutions when we have a defined quantity of a resource, a defined period of years in which we can extract that resource, and information about our marginal benefit, marginal cost, and time preference. What I'd like to do now is move on to that second bullet point, thinking about the price of scarcity, specifically being the marginal user cost. And so we're going to return to that concept of opportunity cost, which is that Econ 101 term that we discussed a couple slides ago, which is just shorthand for what we have to give up to get more of something else. And so the marginal user cost is going to be the opportunity cost due to increasing scarcity in the future attributable to your extraction decisions at any point in time or consumption decisions. And so shorthand here, consumption today reduces what is available tomorrow. And so the marginal user cost then is the present value of foregone future opportunity at the margin. So here focusing on the margin, marginal, a little bit more, a little bit less, really where we think of efficiency in economics. And so you can think of the marginal user cost as being the cost of an additional unit of future consumption foregone, once again, think about that opportunity cost, due to an additional unit consumed now. And so if we don't take into account the scarcity which our decisions create, we are going to be making inefficient decisions and over-consuming in a particular time period. And so our marginal user cost then is going to be identifiable by calculating the difference between the price at which we consume a good and the cost which that same unit of consumption takes to extract. And so once we start talking about non-renewable resources, this marginal user cost concept is going to become more important. But for now, let's just think of a relatively simple example of areas dealing with water scarcity and the difference in the per unit cost of extraction or production of that water and the price at which water will be purchasable on the market. And so the marginal user cost is going to be greater if the demand for that water increases sufficiently to drive the price of it up. And as many of you may know, one of the largest draws on water consumption in places like California, Arizona, is using it for external landscaping, not for what we think of as being more important reasons like drinking or sanitation or flushing waste. And so the marginal user cost then is going to be higher if we allow for residents to use water for these more intensive purposes, but it's going to increase even more as that water becomes more scarce. So to illustrate this concept graphically, let's just quickly return back to our framework from earlier in the lecture, where we had a marginal benefit curve, a marginal cost curve, and a defined number of years, being 2 years, with a time preference or a discount rate of 10%. And so in this setting, remember, we had slightly over 10 units consumed in period 1, slightly under 10 units consumed in period 2. And the present value of the marginal net benefit was equal for both of them. Now, if we were to take those quantities that we calculated using the dynamic equimarginal principle, and we were then to transport them back to a more static world where we have our marginal benefit and marginal cost curve, we can find the price which would be associated with each of those quantities. And so remember that while the present value of the marginal net benefit curves were different in period 1 and period 2 because of the discount rate, the marginal benefit, the underlying static demand curves in each time period were going to be the exact same. And so if we would plug our quantities into those marginal benefit curves, we would find that the price of 10.238 units in period 1, the per unit price was 3.905. And in period 2, the per unit price of 9.762 units extracted was going to be 4.095. Now, the marginal costs of extraction were the same in both time periods, and since we said that marginal user cost is going to be the difference between price and the marginal cost, that's going to imply that that difference is going to be greater as the price increases, and the price increases in the second time period because the quantity decreases, and due to the law of demand, lower quantity, higher price. And so we can then see that the marginal user cost is greater in the second period, 2.095 versus 1.905, in part due to that greater scarcity, which is imposed in time period 2 as a product of greater extraction in time period 1. Now, in equation form, we would actually need to use the information about our marginal benefit curve and the quantities that we calculated using the equations earlier in this lecture to calculate the price, the per unit price associated with that unit of consumption. But once we calculate that per unit price, then we know that marginal user cost is just that per unit price minus the marginal extraction costs. So this just reflects the same information from the previous slide, but on in an equation format rather than a graphical format. And so I think there's going to be a little bit of confusion because when we have the dynamic equimarginal principle, we're setting the present value of the marginal net benefits equal to each other. However, the price and the marginal user cost change over time. And really the reason for that difference is because the price and the marginal user cost don't take into account discounting, whereas that present value of the marginal net benefit takes into account a discounted marginal net benefit curve. And so what this implies is that even though the present values are equalized of the marginal net benefits, the nominal price of the resource is going to increase over time as the resource becomes more scarce, which is what we would expect with fossil fuels. So that wraps up our introduction to resource economics and our exploration of dynamic efficiency. Next week, we'll return to resource economics to apply this concept to the specific topic of non-renewable resource economics, where we're thinking about the extraction and mining of minerals and rare earth metals, as well as fossil fuels.